I will be doing this presentation in English because I understand that there are people who don't prefer Dutch, and most of the terms that I'll be referring to are in English. Therefore, sticking to English is the easiest for me. So, for the people who don't know me, I'm Mats Onselaar. Worked here for a couple of years now. Have a background in mathematics and some animation, and I seem to have some experience with vector math, and I want to share it with you. So let's begin. Also, if you have any questions during any time of the presentation, or you think I'm speaking way too fast, let me know. If I get excited, and this is mathematics, so I can get very excited, I have a tendency to speak a bit too fast, so let me know. So we'll be going over a couple of things, such as a couple of definitions when it comes to vectors and matrices. I'll discuss a bit how you actually calculate with them, because it is mathematics. Simple addition and subtraction work, albeit slightly differently. Then we'll be talking about triangles and circles, which may come up more than you think. Finally, some applied vector math and actually how to use it in your applications. So, about this workshop, the reason for it is we've actually started doing quite a bit of serious games and simulations, and we're using Unity a lot. And also, as you're noticing, I'm being quite verbose on my slides. This is mostly as a reference guide if you want to use them later on. I'll be saying more things in there on the slides. You don't have to read all of it. So the 2D and 3D mathematics can be a bit tricky to understand. So what I'm trying to do is introduce the mathematical concepts in a way that you can get that sort of mathematical reasoning about vector spaces and how to do the operations. So hopefully you can feel a bit more secure in what you're doing. So vector calculus. I took the definition from the internet. It's a branch of mathematics concerned with differentiation, integration of vector fields, primarily in three-dimensional. No, this sounds way too difficult. Actually, we're not going to do that. It's incorrectly called vector calculus, but we're actually going to be doing linear algebra and trigonometry. So what are those? Well, linear algebra, once again, internet definition, it's isomatrix. That might come up later. So basically, we're just going to be multiplying vectors and matrices and sort of moving things through two-dimensional, three-dimensional space. That's mostly what linear algebra is about. So trigonometry, I just took the definition again. This one Alex might disagree with because it's apparently not correct Greek, but this is what the internet says. So basically, it's about triangles and circles and what they do in your 3D space. So that's, I think that's enough introduction. Let's actually get to the context and why we want to use this or when we want to use this. So yeah, for the people that have a background in the standard enterprise applications, which I think I spot a few of you in the room, you don't necessarily use a lot of vector math. There's no 3D space in an enterprise application which just sends messages from one point to the other. So true, it's not relevant there, but like I said, we have been doing some other things, and it does come up in things like animation, where I have a slight background in, geo IT, so robotics, simulation, computer games. So anything that involves a 2D or 3D environment, you will have to use vector math in it somehow. So yeah, about Unity, we will do the assignments in Unity, even for the people that are not necessarily interested in Unity as Unity. But I think it's a great way to visualize the vectors and what you're doing. If you're applying a vector by applying it to another vector and you're moving something, where did you move it? What does it look like? I think Unity helps visualize that, and that's a lot better. So if you don't have Unity yet, please, this is your final chance, because after this I'm just going to be going through everything else. And finally, one question. How many of you are actually interested in just the math for the math and not necessarily Unity? Because can I see a show of hands who just wants to have the math? No? That's great. Then I can skip through a couple of slides. Oh, both. Ooh. There are a couple of concepts which Unity doesn't necessarily keep into account. So I will explain the math, particularly multiplication, I will explain it. But keep in mind that if it gets too complicated, just forget about it. Unity doesn't work in certain ways. So I think that's enough definitions. So lines and points, vectors, matrices, scalars, vector properties. Let's just jump right into it. Differences between vectors, lines, and points, because these get confused a lot of the time. A line is a vector, and points, what is that? So a point is just a singular point in space. And a line is an infinite line crossing through an entirety. And it just has a definition, like it crosses through this point and it has a certain slope. That's a line. A point is just this point. But a vector is a specific direction and a length. So this vector might be pointing to that point if you take it from the origin, but this vector is that vector. They're all the same. Doesn't matter where they are, a vector is a vector. And this might be important. So let's see. Vector, actual definition of a vector. So it has a length and a direction, but no position. So all those vectors I just showed, they were the same thing. Points, like I said, could be seen as a vector from the origin. And confusingly, indeed, in most applications, such as Unity, a vector is used to denote both a point and a vector. So they're used very interchangeably, but the concepts are actually different. So I will refer to vectors as such, with the nice arrow on top of it. And this will hopefully illustrate that I'm indeed talking about vectors. So they're used for position and movement in spatial environments. And this basically means that if you want to go in a certain direction, that is a vector. If you're just at a specific location, that's a point. So what is a matrix? I could insert a picture of Morpheus, but I will not. It's a grid of numbers. And this is where it starts getting, well, slightly unusual for people who are just used to normal arithmetic. This is the array. And for people who are experienced with programming, two-dimensional arrays, not super special, but we can do some interesting operations with them. I will denote them with capital letters. Welcome. I will denote them as capital letters. And they are typically used for rotation, if you want to use them in vector math. So, like I said, matrices don't actually come up in Unity. They've been hidden away by other concepts. But for actual vector math, where you're trying to rotate, matrices are necessary. So a vector is in fact a matrix. It's just one with only a single row. So here you can indeed see a three-dimensional vector with the coordinates for x 7, y 8, and z 9. I have chosen to only use the row vector because I think that is how we define a vector. We don't define it in column beneath each other, even though mathematics, if you look it up online, will often assume a column vector, which indeed would be 7, 8, 9. Why does it matter? I'll get into that a bit. So scalar, it's just a number. This doesn't have nothing to do with vectors, but it's just a number, and I'll give an example. 42. I mean, easy example. So vector length. Here we actually start getting to using vectors and calculating things with them. So I like definitions online. So the length of vector is the square root of the dot product of the vector with itself. Now, I think square roots may sound familiar, but I think to a lot of people dot product is not familiar yet, but I'll get to it very soon. But basically what this means is, well, we just want to know the length from here to here. Well, I mean, if we know that the difference in x is 4 and the difference in y is 3, then I think some people will already be thinking, hey, Pythagoras, I think you could do something with it. And indeed, that's just the vector length. You take the difference in the x direction, you take the difference in the y direction, you sum the squares, and then you take square root of that. That's just Pythagoras, and that is indeed the vector length, as one would expect. So in Unity, if you want a nice reference, it's just dot magnitude. That's how you get the length. So, unit vector. This is a special type of vector. It's a vector with length 1. So that means that the only thing different about this vector with any other vector, unit vector with length 1, is the direction in which it's pointing. So if you're comparing things, then you're only comparing them based on the direction and not on the length or anything. So if you want to compare the direction, use unit vectors. So how to calculate them in Unity is very easy. You just do dot normalized. So, I promised I would get back to it. It's there. Don't worry. So, seems like the normal sort of operation you're expecting. Addition, subtraction, multiplication, division, and the special one I already mentioned, dot product. So, let's get to addition. So there's a special rule when you're trying to add vectors together, and that is they need to be exactly the same dimensions. So the resulting matrix or vector will be the same dimensions as the ones you put in. And every coordinate of the vector will be the sum of the other two exact same coordinates from the original. Adding a vector typically, in terms of vector math, will move something because you're adding a position. So if I mean, this is great if you're having arms. So if you have a point here and you're adding this vector to it, then you're basically moving it to here. That is what adding a vector does. So some examples. How the addition here works is you have 1 in the top left plus 5 in the top left is 6 in the top left. And then 2 plus 6 is 8, 3 plus 7 is 10, etc., etc. So if we try to add two matrices or a vector and a matrix together that have different dimensions, then we're not going to do something like 1 plus 5 and 4 plus 10. And then, no, we just say doesn't work. That's just the definition. We don't even try. It's just wrong. Can't happen. So this is how you usually would add vectors together. Same thing. You just add the 1 to the 5 is 6. 7 plus minus 10 is minus 3. Minus 2 plus 4 is 2. So
there's a question behind.
Yes.
So in vector math, you always need to have two vectors of the same amount of rows. But in pure matrix math, can you actually add two matrices of different sizes?
No, they need to be exactly the same size. Otherwise, it doesn't work. But here we're adding two matrices of the same size. So just to make sure that everybody understanding it. What's the top left? Anyone? 7. Okay. Top right?
Minus 2.
Minus 2, yes. Bottom left? 1. Okay. 3. Exactly. Very quick. It's nice. Okay, so subtraction. It's the same rules as the addition. It's just like you would expect. Adding something and subtracting something, they're two sides of the same coin. So the only difference, of course, now you're subtracting the individual values instead of adding it together. So as one would expect, 4 minus 3 is 1, etc., etc. This is basic. This is like primary school. It's fine. I won't go into this any deeper. The reason why we want to know what subtraction is because it's a target vector. Basically, what is the required movement to go from A to B? So it's something that will come up later during the applied vector math. It's one of the simplest things you'll ever do. But now, multiplication. And this is the one I would skip if everybody wholeheartedly said, please forget about it, because yeah, it's slightly more complicated, and this image will illustrate why. So basically, the rules here for multiplication here are such that every coordinate is this multiplied by that multiplied by that for every coordinate, for every row, for every column. So let's see if I can put it in a little slightly more concrete words. Oh, yeah, no, those are quite complex rules. So basically, what we're seeing here is that the amount of columns for the first matrix A needs to be equal to the amount of rows for matrix B. That's the first rule. Amount of columns must be equal to the amount of rows of B. So the resulting matrix C will have a number of rows equal to the amount of rows of A. So this is the amount of rows comes from A, amount of columns comes from B. So it changes shape. So you were asking about, can you change shape or can you do something with? No, multiplication does, and that's why it's complicated, because you need to wrap your head around that things change. But every value in the coordinates, so here every value, is essentially a dot product. Well, I'm bringing up dot product again. I should get to explaining it soon. Rest assured that this is something you can check afterwards, or maybe we should need to practice for it a little bit. Let's try it as well. So one other type of multiplication is scalar multiplication, which is just multiplying a single number times a vector or a matrix. Then you just multiply the entire thing by that value. That's simple enough. But yeah, maybe we just need to give some examples. I think that might make it a little bit clearer. So here we're seeing that there is indeed 2 columns and 2 rows. Okay, so at least it's allowed. So we get 3 times 2 plus 2 times 3 is, well, 6 plus 6 is 12. And here we get 1 times 2 plus minus 2 times 3, which is 2 minus 6 is minus 4. Okay, so you need to pay attention to that a little bit. If we try to do it the other way around, however, we have 2 columns and only 1 row. It's not allowed. We stop immediately. That's an error. We do not allow that reversing, which in normal math you're allowed. 6 times 9 is 9 times 6. Here, not the same thing. It just plain doesn't work. It gives a different result. So, who's brave? Who wants to try this? Anyone can give me the top left value.
1.
1? Yeah, okay. Top right. 2? Yeah. Bottom left? Yeah. Bottom right? I mean, there might be a pattern going on.
It's big 4 because of the zeros.
Exactly. So this is actually a special matrix. It's the identity matrix. It just preserves the entire thing that you put in on the left side. But still, it's nice to sort of go through the motions of how to multiply well, the different things. So let's do a different one, slight twist. What's the left coordinate?
4. No, that's
7.
13. Oh, sorry, no, it's 0.
7.
Yeah, 7.
I heard 7. It's indeed 7. And the right one?
4.
Indeed. So because I inversed it, it's indeed, it changes rotation. So, I mean, this is, it takes some practice. We won't go through that all now, but it is just another operation that once you get your head around it, you can work with it. So now we get to multiplication unity. It doesn't use these sort of matrix multiplication, actually. It just uses other things. So the only relevant multiplication for unity is a scalar multiplication for vectors. Nothing else, because matrices don't exist. So, like I said, vector multiplication, you just multiply the entire thing by 2, and multiplying by a half or dividing by 2 is essentially the same result. I hope this is clear. So division, because if you have multiplication, it makes sense you have division. Well, it's not that easy. So it is technically possible, but not always. So you need a specific type of matrix in order to be able to divide by another matrix, and that is just not relevant to any of this. So I will not even bother bringing it up after this. If you really want to know about it, just come see me afterwards. I like talking about math. I can give some examples. Not going to do it now. So there we are, finally, dot product. So it only works for vectors. This does not work for matrices, but luckily you're mostly interested in vectors, so very clear. It has a special, interesting property. So what you're doing here with the dot product is you're essentially comparing directions. If they're pointing in exactly the same direction, or at least in the same direction in general, you'll get a positive value. If they're perpendicular to each other, you get exactly 0. If they're not pointing in the same direction, but the opposite direction rather, you get a negative value. Here, because we're using special vectors of exactly length 1, and they're pointing exactly the same direction, we get 1, 0, and the opposite, -1. So here what we're doing is we're comparing direction. So this is the exact formula. You're taking every individual coordinate, multiplying it with the other one. So this may seem similar to Pythagoras. And like my original definition was indeed, it's the square root of the dot product of a vector itself. We're essentially calculating a sort of like comparative length of two vectors. And like I said, it's useful to determine whether vectors have the same direction, because you get a very clear positive, 0, or negative answer. I did not hear any questions, so we will continue with this. Except if you want to know how to use in Unity, which is just Unity 3 ... That's the easy way to know it. Okay. Let's get back to triangles and circles, because I already foreshadowed that a bit. The definitions of triangles and circles, degrees and radians, because some people get them confused sometimes, and some trigonometry rules, so like sine and cosine. So, what is a triangle? Anyone want to give me a definition?
Any
3 sides? Is that enough? 3. Okay, it's you're actually really close. It's not that difficult. It's a shape with 3 straight sides and 3 angles, and the angles happen to sum to 180 degrees. It may sound like a trick question, but this is easy stuff. We know triangles. That's fine. So, what is a circle? I won't ask you this time. I'm giving a slightly more mathematical definition. It's all the points that are exactly a radius r away from a center point in 2 dimensions. If you're talking about a sphere, then it's of course all the in 3 dimensions. Circumference of a circle is 2 pi times the radius. Area is pi times radius squared. The second one you can forget, but 2 pi, that one we're going to be seeing a lot more, particularly when we're talking about the radians. So, degrees and radians. I think this image will illustrate it best. We have the complete circle, and a lot of gamers will be familiar with the 360. So it's a 360 degrees for the entire circle, or in radians, it's 2 pi. Interesting to note is that we go counterclockwise. Mathematicians decided that this was funny to torture people with. So this is the convention. You go counterclockwise for radians. And indeed, every quarter is 90 degrees, as one would expect, and it's just divided equally of the entire perimeter of the circle. Okay, but what can we do with this? Let's first look at a right-angled triangle, because that's a very nice triangle, because it has a right-angled triangle. Right angle in this case, 90 degrees. That's the definition of a right angle. So, yeah, it's a pretty decent triangle, I'd say. So what can we say about this? Well, Pythagoras. That's always a good one. The sum of the squared sides is the hypotenuse, schuine zijde for people in Dutch. But this one may be familiar to most. This one may be sort of getting to some people, maybe like something with these letters might seem familiar a bit. So there's something about the angle and the relation with the sides. Okay, exactly. So in the English it's SOHCAHTOA because hypotenuse instead of schuine zijde, but this may seem pretty familiar for a lot of people. So indeed, the sine of this angle x is equal to the length of the opposite side divided by the length of the hypotenuse. And same thing for the cosine and same thing for the tangent. Okay. Great rule, Mats. Thank you for showing this. But what are we going to do with it? So just a quick reminder for people who didn't remember the sine and cosine, it's the wobbly graphs, the ones that go up and down forever. And they repeat themselves every 2 pi. Tangent, I mean, these ones may seem familiar, I think, to a lot of people. Tangent, you might have seen it, but forget about it. Tangent's not important. We don't care about tangent. So, why do we like a right angle triangle? What is the point of it? Because imagine, if you will, a circle with radius 1. Then we can place a right angle triangle inside of it. There it is. But hang on, we had the rules that the sine of the angle was equal to the opposite side divided by the hypotenuse. But now the hypotenuse is 1. And yeah, so what we're getting essentially is that the coordinates on the circle, on the perimeter of the circle, are given completely by the angle theta. And I'm using theta here because we're already having an x-axis and a y-axis. Don't want to get too confusing, so use a different variable. the coordinates on this point on the circle, because we're getting the opposite side, which is the height of the point on the circle, divided by the hypotenuse, which is 1, the definition of the radius of the circle, which was radius 1. So it just becomes the y value, the y coordinate. Same thing for the cosine. It's the adjacent side divided by the hypotenuse, which falls away. So it's just the x coordinate on the circle. So if you want to know at any point where you are on the circle, just use the sine and the cosine of the angle and you know exactly where you are. Now, the tangent, I've included it anyways. It's basically the perpendicular from the vector of the hypotenuse, but yeah, we're mostly interested in these coordinates because if you want to describe the points on the circle, now you know. So there are some rules about sine and cosine. Let's see if I can keep you interested in them. So yeah, there's no easy way to do this. So these are some rules. These are official trigonometry rules. And this is basically because you started with the sine going down on both sides, or going up in one side and going down the other side. These two are equal. And the same thing for all these rules. Well, some more rules. Tangent is that. And there's a point to this. And I'll get to it. But first I want to just admire that, hang on, this is just Pythagoras. But okay. So, great. You can look these up online. It's not important that I'm showing you these right now. What is important is if you want to go from the sine of an angle to the actual angle itself. And for that you need the inverse sine and the inverse cosine. So, yeah, we have the sine of the angle. We know, for instance, the ratio between the opposite side and the adjacent side. But now we want to know the angle that caused that relationship between the x and the y. So we have, I said click. We have the arcsine and the arccosine. And they're often also used asyn and acos. For which the rule is, if you take the inverse sine of the sine of an angle, you just get the angle back. So in Unity, this is just math f.asyn and math f.acos. Great. The opposite works as well. So if you take the sine of the inverse sine, you get the theta back. But now we get to the rules. Why those rules were important, why they were equivalent to each other. Because if you check a circle and you look at only the top half, then any y coordinate will occur twice, except for the one straight at the top. So if you then want to know which angle caused that y value, there are two solutions for that. So you have the left side and you have the right side. The left side, for instance, being 120 degrees and the right side being 60 degrees. But if you then use the inverse sign, which one is it going to give you? Well, just the one for 60 degrees. It's not going to know that your angle is accidentally 120 degrees. So keep that in mind. Sometimes you get the wrong answer back even though you knew the answer, and that might be because of those rules. There's a duplicity in the answer that you can get, and therefore something gets lost. Similar for people that are familiar with the square root. If you take a negative number and you square it, and you take the square root of that, you get a positive number back and not your original negative number. There's two possible answers, it just gives you the simplest one. So yeah. Slight bit of warning, cautionary tale, if you're ever going to use the inverse sign, keep that in mind. Actually, I'll give a slight hint about that because I'm supposed to be the expert after all. You do know what the difference is between these 2 points, and that is the x-coordinate. If you have the negative x-coordinate or the positive x-coordinate, you can check which one it was, and that can tell you whether it was 60 degrees or 120 degrees. So you can keep them apart, you just need to do that extra step of logic, and that way you can get the correct answer. Okay, that's all great and stuff. That's definitions, that's some cautionary tale. Let's actually apply it, because it was, of course, called applied vector math, not definitions of vector math. So, yeah. Calculating target vector, that's pretty useful. Like I said, it's probably the most common and easy thing you'll do. Moving in a direction. What if you know which direction you want to go, but you want to only travel a certain distance along? Projecting one vector or another. It sounds a bit vague, but I'll show you that it's actually quite useful. Rotating vectors might also come up. perpendicular vectors, intersections between lines, also quite common things, I would say. So yeah, calculating a target vector. Posted the problem earlier, we want to get from point A to point B. What is the way we can get from A to B? Well, okay. So basically we're asking is, what vector V will take me from A to B? Well, I mean, we saw that addition and subtraction works pretty much the same way in vector math as it does in normal arithmetic. So the normal solution would just be subtract A from both sides. That will give me the answer for V. So indeed, we can just do this. It's fine. So here it gives us, well, the vector V required to go from A to B is just B minus A. And that is indeed the answer. So if you want to know what movement you need, that's it. So let's say we know which direction we want to go, but we want to go a specific amount of meters in that direction. Okay, that's doable. First, we need to know which direction we want to go. Okay, that's B minus A, great. But then we want to know what direction, how much, because this might be 60 centimeters, it might be 2.5 meters, it might be 5 kilometers, but we are only interested in the direction. And if you wanted the direction, you needed a unit vector. So to turn it into a unit vector, we need to divide that vector by its length, because then per definition we're getting a vector of length 1, the unit vector. So we divide it by its length, which is indeed denoted by these bars, vector length, and then just multiply that by the distance you want to travel in that direction. That's it. So, and otherwise Alex would get mad at me, I have to mention lerp for Unity. It's similar. So lerping, or linear interpolating in Unity, is you give a start location, a start vector and an end vector, and you say how much of the way you want to go between them. Well, you're basically specifying just how much you want to go from one vector to another, which is typically sort of the direction denoted by B minus A. This one, of course, is based on fractions. The other one is based on actual, like, meter length. Similar, but if you're used to going between 2 points, lerp will definitely help you with that. Okay. So yeah, projecting one vector into another. Yeah, so this is indeed a less common problem, but it might pop up more once you recognize it for what it is. So how long is vector u along another vector v? So an example, maybe, from one of the projects I did, NEO, we have a train track and we have a signal along the track. But we want to know the exact point on the track at which the train passing along the track has passed the signal. But for that we need to know where is the signal actually closest to the track. What is the location on the track for the signal? Basically what we're asking is what's the closest point on the track for that signal. That's vector projection. So we will use the dot product of the unit vectors of u and v. And in this case, u of course is the vector we want to project, and v is the one we're going to project onto. So instead of just traveling a certain distance along a vector, we're not going to travel the entire length of vector u. We're only going to travel the rate at which it is similar to the other direction. And yeah, we want to use a dot product for that. So keep in mind, if we were exactly the same direction, then it's just the entire length of the vector, as we would expect. Then we're traveling the entire length of vector u along vector v. If it's completely perpendicular, well, then the closest point is just the point that we started. Then there's absolutely nothing to add. If they're pointing in opposite directions, I mean, for my example, that doesn't really make any sense, but then you would want to go the other direction. In any case, if we take a look at this image, we're basically interested in, I see some JPEG artifacts, but that's fine. We want to find this point onto vector v, because this is indeed perpendicular, the closest point from where vector u is pointing towards. And the length of this projected vector is indeed equal to the length of u multiplied by the dot product. And dot product gives a scalar. It's not a vector, it's a scalar you get out of dot product. In case I hadn't mentioned that before. Okay, that's projection. Let's move on to something else. Rotating a vector. Yeah, okay, in Unity this works slightly different, but we're doing the actual math as well. So we're going to use something that's called the rotation matrix for rotating in 2D. And this looks like this, basically. And, well, there's our good friends, the sine and the cosine. And one important thing to mention is, if you're looking online for documentation, this is actually a diagonal flip of what you're going to find online, and that's because we're using row vectors instead of column vectors, something I mentioned briefly at the start. For row vectors, this is the one you want to use. So, okay. The order of matrix multiplication actually matters for the result. So, one example would be that if you're rotating this nice bottle, I have an example. If you're rotating it first in this direction and then this direction, it's going to point towards me. But if you're going to first rotate it in this direction and then this direction, it's going to point that way. So rotating, in the order in which you rotate, actually matters for where you're going to end up pointing towards. So, slight important thing to mention. But now let's continue with how we actually do it, rotating a vector. So, well, this is matrix multiplication. It's a vector times rotation matrix. And from this we know, indeed, you multiply, so you get a nice little bit of formula. Yeah, let's just see if we can actually use this in an example. So, who here can tell me from the top of their head what the cosine of 90 degrees is?
That's 1, right? Or is it 0? It's either 1 or 0, but I always forget which is which.
It's 0. It starts at 1. Yeah, sine of 90 is indeed 1. So if we know that the cosine of 90 degrees is 0, then we're going to multiply 0 times x, and then the sine, well, you already said it, the sine of theta is, sine of 90 is 1. So it's 0 times x and minus 1 times y. So, okay, here, I mean, let me just fill in the matrix. Here we're indeed doing that matrix multiplication again, where we're getting minus 7, minus 4. So what we're actually doing here is we're creating a perpendicular. We're rotating it with 90 degrees, as we would expect. And that's what one of the perpendicular matrices looks like. So a three-dimensional rotation, like I already prefaced, we can now, instead of just choosing around only this axis, which for the two-dimensional vector is the only sort of option, we now have 3 axes of rotation to rotate around. And then it becomes even more important that you do the rotation in the correct order. So you have quaternions for doing that in one go. I accidentally clicked. So quaternions allow you to actually rotate around all axes at the same time. But it's kind of difficult. So I'm not going to explain it in proper math. I will only explain it in the context of Unity, which I'll do in a bit. So for proper math, I will stick to Euler angles, which is basically the rotations around separate axes. So, yeah, slightly different looking rotation matrix, but we're recognizing some of the similar pattern as a two-dimensional rotation matrix with the cosine, cosine, sine, negative sign. Because what we're doing here, by keeping the 1, 0, 0, 1, 0, 0, we're preserving the coordinates of x. There's nothing happening to the coordinate of x, as we would expect. We're rotating around the x-axis. And similar to the y-axis and the z-axis. These are what the matrices are. I will not show any examples because that's a lot of mathematics to show on slides, and it's more fun to try that yourself anyways. So once again, order of operations matters. You're going to get different results if you do the rotation in different order. So this one, I think to most people is more interesting, rotating in Unity. So once again, Euler angles and quaternions. And there is indeed, once again, around individual axes and quaternions being four-dimensional vectors. Great. There's a trade-off. Quaternions are nice and easy. You can very quickly call, like, please rotate this to that. And it will give you some magical four-dimensional vector, and that will work. but do you still understand what you're doing? So for me, there's a big trade-off between Euler angles where you're actually saying like this is the exact rotation for this axis, versus quaternion, which would just give you some magical value which should work. So quaternions, to use them, you have the from to rotation where you're saying I have one vector, please give me the rotation from this vector to that vector in three-dimensional space. Or you can say please generate a quaternion that will rotate this much around the x-axis, this much around the y-axis, and that much around the z-axis. So two most common ways, I think, of creating a quaternion. To apply it, you can either just multiply the original vector, pre-multiply the quaternion with the vector to get the new rotated vector, or just set the transform's rotation to the new quaternion. And of course, there's a difference between the rotation and local rotation. For people who have already done Unity, it's this should make some sense, and otherwise I'll get to it again in a bit. Euler angles, which I think are slightly more understandable, you can either cheat and first create a quaternion and then ask Euler angles of that. Great. Or you can just create it by yourself by using a new vector. You apply them by just overriding the Euler angles of a game object. So some other useful function is the look at, which I think gets a lot of mileage. It basically asks a game object, please rotate me so that I'm looking in the direction of another game object. And it will just fix the rotation for you. That's great. That's, makes my work sort of not that important anymore. Another useful function is the spherical linear interpolation, where you basically can actually rotate from one spatial quaternion rotation to another, and then a fraction of that. So you're rotating across a spherical surface, and it can be useful sometimes if you really want to rotate from one rotation to the other rotation. Use that. Don't think about it. Don't try to understand quaternions. It just does the job. Great. Moving on. Perpendicular vectors. So in 2D we already briefly saw it. It was basically, rotate by 90 degrees or pi over 2 in either direction, either left or right. I did that the wrong way around, left or right. So, in 2D. Take the matrix that I just showed you, apply it, and then you get these two things. What you're essentially doing is you're swapping the order of the coordinates of your x and y with a -1 to one of the two, whichever you want to give some perpendicular. You can check my code and occasionally find just the coordinate swap and it does the perpendicular. It's fine. So, example, we're essentially at a 60-degree angle. We want to get those two perpendiculars. We do the multiplication. Great, you can check the slides later. I hope you guys just believe that I know what I'm doing. And finally, you get these coordinates. And of course, as one would expect, the opposite vector is exactly the negative of the other vector. We're mirroring around the origin, therefore it's just the negative of the other. Interesting observation if you hadn't made it before, otherwise. And with that, we get to three-dimensional perpendiculars, which are actually not as easy. And there's a common trope here that every time you add a dimension, it gets a little bit harder for some reason. And the easiest reason for this is that if I have the perpendicular, I have a vector this, like this is the vector. Okay, give me a perpendicular. Oh, this is a perpendicular. I rotated by 90 degrees. Yeah, but this is also perpendicular, and this is also perpendicular. In fact, there's an infinite amount of perpendiculars in 3 dimensions to a single vector. So, you can find infinitely many, and then which one is the correct one? So that's why the problem is essentially that you can't even necessarily rotate around the x-axis, because if you rotate this one, let's say around the y-axis, you just get this. That's not perpendicular. So so I need to rotate around something else. Well, there is a way for this. It's to use the cross product, but it actually requires 2 vectors as an input. So if you have 2 vectors, then you can find a perpendicular vector perpendicular to both vectors together. Well, great. Doesn't come up a lot. But if it comes up, just Google cross product. You'll find nice automatic algorithms that do it for you. So perpendicular vector in Unity, I mean, here I just had a rotational matrix for 90 degrees. Can it be easier than that? Well, yeah, it's actually you have it in Unity straight away. You have your transform. It has 3 vectors for you. Transform forward is basically your game object where it's looking at right now, typically your local z-axis. Then you have your transform right, which is essentially your perpendicular. And I'm doing my right, this is your right. So this is just essentially the local x-axis. And if you ask that one, if you ask transform.right, you'll just get the global right perpendicular for your current vector. So it's a really nice and easy way to get it. Well, to include it so it doesn't feel left out, there's also the y direction, which is the local up direction. But and once again, there's no left, there's no back, there's no down, but you can get it by just multiplying the vector by -1. And there you have it. So, maybe some people were waiting for this, in which case this is your moment. Line-line intersection. You want to find the intersection point between 2 lines, which, well, let's have 2 lines, because like I said, they have a height, which is defined by a certain slope, a of x, a times x, and then we add some constant to shift it up or down. So we have 2 lines, can be going any direction, a, c, b, and d, completely free variables. So if they need to be the same value, we must have the same result on both sides. So ax plus c is bx plus d. Could rearrange this so we can get all the x's on one side. Ax minus bx is d minus c. I hope I'm not going too fast for you. Solve for x. I definitely hope I'm not going too fast for you. You just divide by a minus b. And therefore you're only left with the x on one side. So great, this is x, but then what is y? Well, just plug in x in the original formula of ax plus c, and you get that. Great. If it comes up, that's how you do it. If it doesn't come up, forget about it. So, now we get to the point, and let me just check if I'm actually on schedule, that I've not gone super fast. Yeah, I'm on schedule, that's good. So now we get to the point where you actually implement it in your solution. Because great that you now have some basic understanding of vectors, how to work with them, but now we're going to actually implement it. And, well, yeah, I'll go through some of my, I wouldn't say best practice or something, just like this is how I've done it so far and it seems to work. So maybe it's a decent practice, I guess. So some things, especially for people who've already worked with it, it can seem like a lot of like duh, but sometimes it doesn't hurt just stating the obvious. Sometimes like, I hadn't thought of that in a while. Can be fine. So yeah, using existing math libraries. This should be a really duh moment, but still, just to point it out, most standard programming languages do have some math library available. They will definitely have functions for sine and cosine, but vectors often lacking a bit. So if you use Unity, then the mathf library and the vector2 classes just come straight out of the box. Don't have to do anything with that. But otherwise, the challenge is always understanding what function actually does what. Because if you type mathf dot, then you get this nice list of like 50 functions. Which one do I need? And yeah, that is sort of always the point of understanding what you need to do. And it also counts for the functions like look at. Great, you can use it for a lot of things. I've seen people use it for a lot of things. Also things they shouldn't have been using it for, but there we are. So you can create your own math library because if you have some open source math library, if you just need a simple math library, it's fine. Just make it your own. It doesn't have to take that long. And open source math library with like this hundreds of functions can take quite some time to actually completely understand what every function does and which one you need. So simple functional helper class is fine. Like, oh, I want a perpendicular. It's just a simple coordinate swap. Don't need to put in an entire open source library to do that. Defining something as a vector, even in not Unity, just in normal C#, just defining a vector is not that much work either. And if that helps represent the problem for you, that's the way to go, I'd say. So the goal at the end of the day is just to make the algorithms understandable, because someone is going to read your code, that person wants to understand what you want to do. So if you have to define your own matrix, if you have to define your own vector, if that's the way your data is structured, if that's the way your algorithm is structured, just do it. It just helps understanding it that much easier. So on that subject, while I'm on my high horse, clear method naming. If you're writing these sort of algorithms and you're just naming it like do inverse or something, you need to have clear names. You need to understand what's going on, because there are so many mathematical operations you can do. There's, I take the inverse cosine and then I add 90 degrees to that, and that, of course, if I do the arc sine, then clearly that was what I wanted. No, just make every single step its own method if that helps explain what you're doing. Nobody wants to read 4 lines of comments for every single line of code that you're writing. It makes it impossible to read. So separate methods, method naming, that at the end of the day just makes it more understandable, more maintainable. And once again, this can be a dull moment. It may sound a bit ranty to some people that are already doing this, but at the end of the day, if you're the one that's the one with mathematical expertise in the team, and the other people also need to be able to work with your code, you need to make it as easy for them as possible. So then we also get on the subject of documenting. Just when you're writing a documentation about mathematical algorithm, just describe exactly what you're trying to do. I'm trying to rotate it from here to here because I'm wanting to achieve that. Just some loose operations don't mean anything. So if you're using some standard operation, you don't need to go into full detail of what that operation is. Just link to Wikipedia. Yeah, explaining how mathematics tie in with every step towards the goal. This for me is fairly obvious, but still. Also last one, use images. Here there were a lot of numbers. I like numbers. I think I'm one of the few people that likes numbers. So if you want people to understand it, you need images. So also, this is a fresh slide, the potential traps in Unity. And I already mentioned it. There's a lot of functions. But if you're not sure what you're doing, if you're just summoning quaternions out of the ether for every single problem, and then you're not sure why they still exist and what half of them do, then you're not sure what the result is anymore. So make sure you're using the right functions and nothing more than that. Another interesting tidbit is coordinate systems, and I felt just the need to include this. Math typically uses a left-hand coordinate system, which is that this is the z-axis, this is the y-axis, and this is the x-axis. And indeed, if you rotate it like this, then this looks like an image you'll find on most mathematics literature. Unity uses the right-handed system, where indeed, for people that have 2 hands, you will notice that there's indeed some slight difference between the two. So if you check out mathematical algorithms that are based on which axis you're using, Unity might suddenly have a -1 somewhere because there's one axis that's inverted. Might be interesting to know in case you ever wonder why this is not working. So there's also the slight issue of local position rotation versus global position rotation. If you're working with Unity a lot more, then you might say, oh, hey, I'm going to change the local position of something, but that is local to maybe the object you're impart in the hierarchy, and then you can get unexpected results. Global coordinate system, global rotation, it's different. Keep that in mind when you're doing that. Once again, just don't apply functions left and right. Be sure you have some idea of why you need to do something. I'm not looking at anyone in particular in this case. I'm just as bad without myself when I started out. So yeah, finally, some useful references, because I've shown a lot of things now. A lot of things, a lot of information. And I think 50% of that you can just find online on Wikipedia, if you know what to search for. So here I have a list. The slides are online. These are actually hyperlinks. They'll link you directly to an article. Hopefully you have now enough base understanding of what the notation there is so you can understand what those things do. But I use these as well. If I'm ever unsure of what exactly I need to do again, I just checked one of the pages. They're actually quite detailed. And yeah, another very useful source to finish is Unity API. If you're using Unity, then particularly these four, just check it out. There's a lot of functions in there, and each of them has some description as well. So it's a good source to check out. I think that's me done with the talkingness. Are there any questions? People still feeling okay about their choice for being here tonight?
Let's see.
Okay, that's before we get to the dinner. I have a short sort of explanation about the assignments. There will be two sets of assignments, and you can either choose whether you want the pure math, which uses my sort of custom vector and matrix class, which uses the actual sort of math as I mostly explained it here. And there's a separate set of assignments which is using the Unity inbuilt vector 3 and mostly in math F and stuff functions. So the assignments are also in the repository, but you can choose which one of the set you want to use. The first 9 are almost identical except for using different data structures. After that, one goes more into the more hardcore mathematics, and the other one goes to making interesting Unity objects that move around in nice patterns. So if you have any questions during the assignments, you can go to me, but you can also go to my two lovely assistants, Alex and Sarah, who you might recognize from the first workshop.
Does everybody know where he can download the repo for the ones that do not have it already?
No.
Okay. I will update the Outlook invite with a link to the repo. Yeah. For the ones, anybody that does not have the Outlook invite, I will send it to you and then you can. Yeah.
Has everyone been successful in installing and activating Unity?
By now, hopefully. Okay, good.
No, I could install it, but I get no license or anything.
I will help you after the dinner.
Okay. And of course, if you have any questions about mathematics, don't hesitate to walk up to me and ask some specific questions. I like talking about math, as you can tell, and be happy to help. So thank you for your attention, and I think it's now dinner time.
Yes, and one last thing. The Klaver is also booked as overflow because it's already quite crowded here. So people can also sit in the Klaver after dinner. Yeah?
Thank you.
Don't have to clap. And here you can choose either between so in the workshop 2 vector math, there will be a scenes folder where you either have math, which is just sort of pure math with custom matrix and vector class, and you have the Unity folder. And each of these scenes is a separate assignment. So I'll take, for instance, the Unity 1. Here, okay, it's opened, 1 Unity. So I can play it, and I can see, well, the green ones are the ones which is the answer, and the blue ones are the ones which is currently your result. So the idea is that eventually the blue ones will overlap with the green ones, showing that you did the correct thing. What you will find here is you either, basically, depending on if you chose Unity or Math, you either have the Unity assignments folder here, and there for every separate assignment there is Unity 1 assignment, Unity 2 assignment. If you open that, you should get it in Visual Studio or monodevelop, whichever developer IDE of choice. The only thing you have to do is fill in what answer you think is necessary in the do math function. And the target is described in the comment above the do math method every single time. If you want to check your answer or cheat, I will not judge you. You can check the answers folder, which is just a separate folder. And by opening the Unity 1 answers, you can check whether you did the thing that I was expecting you to do, or if you just want to check your answer, whatever. So if there's any questions about that, don't hesitate to ask. And otherwise, good luck and have fun. Down.
Mats. Ja. Start zeg maar bij het creëren van een project.